I remember that one.
I was looking at
Wait,
them.
did
I
you
like,
remember
but
that?
there weren't. It wasn't a straight order. Like they were like mixed up.
Yeah. Slightly.
Wait,
So like this is
I
general
was
trend.
I was sure it was these two.
Yeah.
It's alright. So we're gonna be continuing with module 3 today. We're gonna crack on.
I got full marks for this.
Nice.
No. Pretty good.
We're gonna do these words today.
Did you write that up? Yes, I wanted to.
We're gonna do these. Yeah.
I don't know.
Not a single thing.
Like I was watching the revision thing.
The revision in the last lesson. Did you be lost in the exam?
Wow, that was
Did you remember last
big break.
I thought you remember last
Two and then
Try it like
made up the grade out. Cold. What did you get right? And then but like the last couple pages, yeah, I didn't get any. Nice to see.
It's a bit tricky at the end. Is there a copy of the exam anywhere for yeah. Exam and solutions? Yeah, okay, perfect, thanks. Yeah, I'm getting an exam printed for you now. Okay.
If the mass lost is 40, this is not that hard. This is not that
You want to do it on the board for us now?
Yeah, no,
Okay.
yeah, I will. No,
Okay.
If I think this is on, I think.
Like, can you wait? Look at the the computer real quick, and can you tell me if it's like, is it right? Is it centered now? Is it actually?
No, it's centered. Oh, wait, no, go back. No, go that way. Bit more. Yeah, that's good.
Centered?
Yeah, that's good.
Yeah. All right. Cool.
So is it the only
Yeah.
markers?
So, yeah, you can use the marker.
It's only 4 marks, right? So it's not that bad.
It's not that bad.
I need the periodic table, please.
Yep. 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 So he's taken my spot. I feel as if my job's been taken right now.
Yeah, well,
The molar mass of the number of moles. Okay, no, sorry. NH2O.
N is just a number.
Yep. Sorry. Yep. Thank you.
Okay. What the hell is AS? Never heard of that element in my life. I don't know how you know all these moral masses
Which ones?
by heart.
Arsenic. I don't know what AS is.
No, like you just write them all mass. You don't have to look at them.
Well, I've been doing chemistry for a lot longer than you have.
Yeah. Oh, wow. Am I on the right track here?
You could be on the right track. You could be onto something.
I gotta find what arsenic is though. Oh, there it is.
Yeah. Do I not give any? Does everyone have materials? Do I give everyone materials? Did I give Kevin?
Students, can you
Kevin, did I give you material?
find your calculator?
Yeah, no. Yeah, yeah.
Yeah.
So are you you done?
Nice.
Okay. Continuing.
Yeah.
Yeah. Okay.
It's a 4 mark question. Like, give me at least like what's the breakdown of the numbers? I don't know.
Low.
I didn't know like what the question even meant. Like, cause I read it. You see this?
Was it? I'll let him finish this and then we'll get started with the lesson. But do you guys have any questions that you want to go through from the exam? Anything? No.
What did you guys all get? What did you guys all get?
I haven't even checked.
Oh.
Damn.
What did you get? Oh, 33. 33. What did you get? Just say.
Only say if you're comfortable saying.
Higher or lower? Oh, okay.
What's the question?
So, no, but what is the dot and then why is the end not even
It's
a
the
capital?
it's the what is the crystal
yeah.
action?
See, he's good.
It literally tells you.
So you've drawn yourself. Okay.
So the mass loss. Nobody is listening to me.
I don't know what you've done here.
The
You've
mass
written.
loss during this process is 40.42% of the original. Therefore, n times 18.016 equals 0.42. No, 0.404. Did anybody get this question?
Yeah.
Who's listening to me?
So, someone in this class got the question correct.
Orlando got 68, Daniel.
That's pretty good.
Yeah, he's lost 2 marks. Someone got full marks in this exam. Someone got full marks in this
I
exam.
got 0 marks.
Yeah. Huh?
What's that?
Yeah, Zihan Feng.
I think I feel like I've heard of this.
You felt like you've heard of him?
Yeah. It's probably goes to do or something.
Yeah, maybe.
Nah, like some of these kids just kept saying they're not even good at maths or anything else, they're just good at chemistry, right?
Yeah, what's wrong with that?
Nothing wrong with that.
So that means that
She
if I
just added.
subtract that from that.
Yeah, no.
No, it's okay. We have lots of vegetables. I put it.
So no questions you guys want to go through?
I didn't
Was that the lowest
I
one
didn't
you
put
got?
the right one. That's hilarious.
No, the lowest. I don't remember.
Do you remember? I remember lowest one
Yeah,
you
this
got.
is easy. This is a simple calculation.
Do you want me to check?
Yeah, I did.
I feel like I had.
But then I went back and I was like, wait. I remember. No, I did N and C. I went back and I was like,
God, this is easy.
no, that reminded me of something I did once.
Shut up.
No, you see all this.
Yeah,
That was
Seven.
when I thought it was.
Nice.
Is that the
Yeah,
answer?
good work. Good work.
Just make me a teacher already.
Do you want
Why
to?
are you getting paid to teach me? I should be getting paid to teach you right now.
All right. Sit down.
So first of all, I don't know what the dot means. I don't know why is there
Okay. Is there any questions that anyone wants to go through?
It says it's
Yes
the water
or no? Or we can just talk about the lesson.
It's the water.
Yeah, let's just get started with the lesson.
You did not even know what they were. You just need to
So if anyone was confused about the last question, we have a great explanation here from Daniel. Yep.
You're welcome, guys.
Harvard student.
This is like the only question I got full marks for. I can't
Yep.
lie.
Nice. Okay, I'm rubbing it out.
Well, actually, no. Never mind. I didn't get full marks.
All right. So just one last time. No one has any questions that they want to go through? Okay. If you have any questions throughout the course of this class, feel free to let me know and we can go through at the end. But let's just quickly recap what we got up to last term before we took a little break. So we're in the middle of module 3 right now, talking about like chemical reactions and all that sort of stuff. Today, what we're going to be learning about is galvanic cells. But before we do that, we're going to be do a quick recap of the principles that we need to understand galvanic cells, which was principles of reduction and oxidation and metal reactivity. So, before we get into that, metal reactivity. This was a question in the exam, actually, if you guys remember. So, metal reactivity, if we remember, has to do with what kind of reactions the metals typically undergo. Like what kind of bonding the metals undergo, typically. Starts with I. Ionic bonding. Yeah, cool. Yeah, nice. So ionic bonding, right? So what do metal What do metals do in ionic bonds? What do metal atoms do?
They swap, they give.
They give electrons away, right? So they don't want to keep their electrons, right? They have too many for less stability, right? So in saying that, if you remember this idea of metal reactivity, a metal's reactivity is determined by its ability to give electrons away, right? So in saying that, removing an electron from a metal has direct, I guess, relationship with its reactivity, right? So in saying that, this comes back to ideas that we learned in Module 1 of like ionization, if you remember that. So do we all remember the idea of like ionization energy?
I do.
What's ionization energy?
The energy required to remove the first electron from the shells.
Okay, cool, right? So basically, like the amount of energy required to remove an electron from like your valence shell, right? So what was the general trend of our first ionization energy? What principle do we use to explain it? Effective nuclear charge. And what is effective nuclear charge?
The charge that the nucleus has on the electrons minus the shield.
Yeah, right. So the net positive charge that we have from your like the nucleus to your electrons, right? So that includes the electrostatic attraction from your nucleus, let's say, is here, and then you have your electron out here, right? So then let's say you have a bunch of shells here, right? So you have net attractive force to the nucleus, but you have to subtract these little repulsive forces from, for example, electrons here, right? So what was the trend of effective nuclear charge across the periodic table? So yeah, so we increase, so Z effective increases from left to right. What about down and up a group? So you're saying it decreases down a group. So why is this? How do we explain the increase across a group? Across a period.
So every time you add a proton or an electron, obviously when you add the proton, you increase the pool that the nucleus has in electrons, and also when you add an electron, is it when you add an electron you decrease shielding, or is it the other way around?
So what's the effect of shielding? Is it not centered?
Can you not tell?
Well, I asked my my lovely student here if it was centered.
It's on the OBS.
Oh yeah, true. Looks a lot better actually. Thanks. Guys, I'm getting fired. I trusted you. Anyway, so yeah, so shielding, if you remember, is then like it's the effect from the repulsion of like electrons, right? Because they have the similar charge, right? So this electron here will have a net repulsive force on this electron, and like the same thing with like this way as well, right? So when you add in another electron, you do get a little bit of shielding, right? But it's like, if you think about it, an electron shielding from within as opposed to like in the same shell, it'll have different effects, right? So again, electron here, if it's experiencing an effect this way, which is directly in opposition to the attractive force, is likely larger to have a larger effect than an electron getting added here, right? Which is then, if you look at like, for example, this repulsive force, it's not as effective as that, right? But the effect of adding a proton is that all of the charge in the center here acts on each and every electron, right? So the effect of adding in a proton is larger than the effect of the shielding effect gained than an electron, right? So the net effect as you move across a period is that you get an increased effective nuclear charge as a result of the larger net positive charge, right? Cool. What about down a group? How do we explain down a group? So what's the main thing that changes down a group?
Is this the marking criteria?
Yeah, it's the solutions, I guess. What's the main change that we have as we go from one group to the next in the periodic table? We add in one really big circular. We add in a new shell, right? So it's effectively like comparing, let's say a nucleus, it's effectively comparing an electron here to an electron here, right? So there's two things that actually happen here. First of all is like, technically yes, when you compare this first electron to the second electron is going to, like the absolute amount of electron shielding that's going to experience is larger, right? Because it's fundamentally further out, which means that these electrons become more inner electrons, right? So the electrons that, for example, if you consider this electron, the electrons in the same shell here when we consider those same electrons, for the outer one, they become inner electrons. So the net direction of the force is more outwards, right? But also in saying that, what happens is as you go further out, distance is a really big factor in electrostatic force, right? So as you increase the distance between your nucleus and your electron, your electrostatic attractive force also decreases, right? The combination of these two, with comparison to the effect of just adding in a couple more protons, the net result is that you have a decrease in effective nuclear charge, right? So again, effective nuclear charge, the trend in terms of how it increases is like this. Yeah? So top right will have the highest, bottom left will have the lowest, right? So what does this have to do with metal reactivity? How do we relate this concept to metal reactivity?
The first ionization energy or the effective nuclear charge?
So how does first ionization energy relate to, like, I guess, effective nuclear charge, first of all?
You don't want to, if you have a higher first ionization energy, then you don't want to be losing electrons. You want to be gaining them.
Okay, so how does this relate to the trends in effective nuclear charge?
Metals are on the left, which means they have a lower effective lower first ionization energy, which means that they want to lose electrons more readily, which means they create cations, so then they can bond they create cations so they can bond better.
Sure, so this is like comparing metals and non-metals. But when we compare, I guess, first ionization within the metals, right? Because we're talking about the difference in reactivity between metals, right? So importantly, the fundamental idea here is that effective nuclear charge is, again, kind of like a measure of how tightly your electrons are being bound to the nucleus, right? Is it easier to remove something against a greater or lesser force? Obviously, it's easier to remove something against a lesser force, right? So with effective nuclear charge, the higher the effective nuclear charge, is like the trend in first ionization energy the same or different?
Yeah, same.
Why is it the same?
Because it requires more energy to remove it, it has more force.
Yeah, right, because a higher effective nuclear charge means that you require more energy to remove that electron, right? So in terms of first ionization energy, it has the opposite direction. Does that make sense, everyone? Yeah. So then how we relate this to metal reactivity is that the lower the first ionization energy, the more readily your electron is able to be liberated.
So wait, isn't it in the same direction?
So effective nuclear charge, the higher, oh, okay, yeah, like, I guess. Like, this is the amount of energy, I guess, is, the amount of energy required to remove is in the same direction. But in terms of metal reactivity, right, you want to be thinking about in the opposite direction, right? Because, again, a lower first ionization energy means less energy required to liberate, means more readily able to react, right? Do you also remember this idea from last term a little bit? Yeah, hopefully. And then we talked about metal reactivity, right? So if you remember, we had that reactivity series, which hopefully you've remembered some of. But we're going to be using the periodic table today. But we remember that more reactive metals displace less reactive metals, right? So if you remember last time, we would have talked about that example where let's say that you have like a beaker here, right? And you have like, I don't know, it's like, is there an example in your books? I think there is, right?
What's displaced?
Sorry?
What do you mean displaced?
Displaced. So if you remember what happens with metal reactivity, right? Let's say you have, let's look at the example in your books here. It'll illustrate it a bit better. So you have copper and zinc, basically. So the initial reaction here is, if you were to write it out, it's zinc solid plus copper sulfate solution, right? So this is your reaction equation, right? And what happens finally is your copper gets displaced from solution, so it comes out of solution, right? So here it's in its aqueous form, it gets displaced, so it comes out of solution and becomes solid.
So why is that?
Hmm?
So why is that?
So that happens because your zinc is more reactive. So in terms of reactivity, reactivity only really comes into effect when you have like ideas with bonding, right? So because for something to react, like for your zinc, because it's more reactive, what it means is it's gonna, like, the sulfate is, like, the way I think about it, it's gonna more preferentially bond to zinc than it is to copper, right? So this zinc here, because it's more reactive than copper, kicks it out of solution. So you can see initially it's copper in solution, then it's zinc in solution after
So
it.
if you have a metal in solution and then you put a more readily reactive metal in that solution, it's gonna swap.
it gets displaced. Yeah. And then the one that gets displaced, it comes out as a solid. Yeah. So if you look at the example here, you can see that so copper I guess is I don't know if that's the correct colors. Copper is typically blue, but we'll just let that slide for now. But the idea is that different metal ions in solution will produce different colors. Right? So that's what you can see happening in this example. Right? Because zinc is displacing copper, you have a different metal ion in the solution, which gives your solution a different color. Right? It's similar to like the ideas of, you remember when we talked in module 1 about the flame test, right? You get different colors because of the different properties of like innate properties of metals, right? And you can see here that like this is like a really extreme illustration of like the changing of the solids. But what you would normally get is like, let's say this is like initially like zinc, right? What would happen is like this like top part here would probably still be zinc, but this bottom part here that's in solution, this part would probably become copper, and the copper would displace over the zinc, like little like the bar. That's what will probably happen in like theory.
Oh, wait, so the part in the water, the part in the solution is gonna become.
Yeah, the copper is going to like kind of like consolidate on top of this little zinc bar.
Consolidate on top.
Yeah, so like it's like this bar initially is like all zinc, right? So it's like the zinc is going to get displaced off, and the copper is going to consolidate on top of this.
The whole block.
Like yeah, on this block. Probably not the whole block is going to turn copper, right? But at least the part that's in solution is probably going to like.
Would it penetrate through the whole thing or just the outside?
I imagine it would just be the outside, right? Because after the outside gets like the copper comes, then it can't really react with the zinc anymore, right? But you guys get the idea of like the copper coming out of solution, right? So that's like what happens in terms of metal reactivity, right? And then like now I guess it's more applicable. If you look at our periodic tables, then you have that whole series of like reduction, which we'll look at today. That's what we're learning about today. Top to bottom is in order of like basically reactivity and displacement, all that sort of stuff, right? Hello. That's right. That's right. Okay. Exam. And today's semester. Okay, so now we've gone back over metal reactivity. Let's go back over redox, right? So what do we remember about redox? Do we remember the like
Reduction and oxidation.
oxidization?
Why do you not do this test if you know?
Oxidation, right? So what was our little like 6 letters that we were to remember?
RED space.
Huh?
Or it's just this-
So it's like oil rig, right?
you take formula for one instead of the two.
Right? So oxidation is loss, reduction is gain. This refers to electrons, right? So if you use this example, zinc, copper, there was a pretty tricky question in the exam about like reduction, oxidation, if you guys remember. There was like that question about iron.
Yeah, Fe to Fe, and then that.
Yeah, there was a question.
Spoil the exam, some people just remember it.
Okay. And then so if you remember, oxidation meaning loss of electrons. So when we compare for redox, we want to look at both sides of the reaction. We want to compare what species have changed in oxidation state and what has stayed the same, right? If we look at both sides of this reaction, for example, you can see that zinc, you want to look at the most important thing you want to look at is basically the charge, right? Because if there's a change in charge, it means there's been electron transfer. Zinc here, what's the initial charge? Neutral, right? What's the charge of zinc after?
2+.
So if we compare before and after, we have zinc is 0, zinc is 2+. Copper is, what's initially?
2+.
What's copper after? What's sulfate?
2-.
What's after?
Still 2-.
Yep, okay, good, I've written it. But you can see here that sulfate nothing's changed to sulfate, right? Which means it hasn't undergone reduction or oxidation. It's just been like left there, basically.
Wait, but if sulfate goes under reduction or oxidation, then how would you even know the charge of the other two metals?
How would you?
The only way I knew the charge of the metals was because I knew that sulfate was 2-, but if it wasn't 2-, like if it changed, how would you know the charge of the metals?
If
It's a bad question.
so, the polyatomic ions generally won't undergo
Oh, okay.
It's mainly just because the metals they undergo because of their differences in reactivity, if that makes sense, right? But so if we look at here, what's changed to go from 0 to plus? What's the like change in electrons here? What has happened to your zinc?
2 less.
You've lost 2 electrons, right? Zinc solid has lost 2 electrons to get to zinc 2 plus here, right? So what process has zinc undergone? So zinc has undergone. No. What? Zinc has lost electrons.
What's reduction?
Yeah, I don't know.
So oxidation is loss, reduction is gain. That's what oil rig stands for.
Wait, oxidation. Can you just say that again, please?
So if you look at oil rig, fundamental, I still think about this to this day.
Okay, that's good.
Oxidation is loss, reduction is gain.
Oxidation is loss of electrons?
Yes, of
Or
electrons.
charge?
Electrons.
Oxidation is loss of electrons. Reduction is gain of electrons.
Yes. So if zinc has gone from 0 to 2 plus, it's what? Lost electrons.
So it's oxidization.
So it's undergone oxidation, right?
Is it oxidization or
Oxidation. Yeah, which makes it, if it's undergone oxidation, it makes it the,
Oxidant. I'm just taking a guess.
it's the other way around. It's the reductant. It makes it the reductant or the reducing agent.
I thought like oil rig was part of the example.
Well, it kind of is part of the exam.
No, like part of the example. Like
Oh.
an oil rig and then there was like some chemicals in there.
Okay.
Now,
Yeah, that's right, that's right. And then so,
Loss, reduction is gain.
yes, then we look at the other species. Copper 2 plus has undergone reduction, right? And it's the oxidant slash oxidizing agent. Does that make sense to everybody? That was explaining metal activity.
Let's write that down. So zinc has undergone oxidation,
Zinc has undergone oxidation,
makes it the reductant.
which makes it the reductant. Oh, I don't know, man.
What is a reductant? What does a reductant do?
It. What?
Like, why is it a reductant?
questions are really bad.
Why is it a reductant?
Yeah, like, so,
Because it reduces the other thing.
like, what I want to know pretty much is why they had to create a name.
Yeah, I don't know, man. Like, it just means if it's the reductant, it reduced the other thing. It caused something else to undergo
It
reduction.
experienced oxidation, which means that it reduced something else,
Yep.
which makes it a reductant.
Yep. Or the reducing agent.
Okay, but knowing that does it actually help you answer any questions, or is it just there to like?
So the reduction is the oxidizing agent.
The reduction is not the oxidization. The oxidation, not oxidization.
No, but what is reduction and then you got so reduction and oxidation.
So it let me write undergoes oxidation, undergoes reduction. So it's known as the oxidant or the oxidizing agent because it oxidizes the other thing.
That's paradoxical.
Okay, you bring it up with whichever scientist named that. Does that make sense to everyone though? Are we sort of re-familiarized with these ideas after yeah?
Wait,
Okay.
we actually learned it.
Guys, we learnt this, right? Yeah, we learnt
I
it.
remember like I specifically remember like not listening during this.
Yeah, thanks. Yeah,
No, but
thanks.
this year I'm actually not.
No, I believe you. Yeah, no, I believe you.
Because I don't know.
Yeah,
So
okay.
I kind of have to listen.
Yeah, nice.
And this is like maths year and the next year is chemistry.
Yeah, no, but like I'm not.
So why is my board turned off?
I can't just go on and on.
What should I do, guys?
You got 3 marks, it's cold.
Oh, it's back. Okay, so what are we looking at? We're looking at a practical application of redox. And if you guys have ever heard of galvanic cells, that's what we're looking at today. Okay. Can I rub this out? Yeah, okay, cool.
That puts me in a good spot. Brian, you, Tom, and David. Yeah, because they're not putting any like. There's no necessarily risk for me. If I'm behind Ryan, there's risk. If I'm behind Nicholas Lake, there's risk.
But I didn't know this Nicholas
I've never heard of him before. I've never seen his face.
No, but like he got the same as you and then he got 60. So like, I mean, he might actually be smart.
Yeah, he could be, but still.
Ethan Zhang said it was
I don't want someone
Okay.
to be ahead of me that's like. I might be better than him, but someone who's ahead of me is definitely going to do better.
Okay.
I know you, Tom, Lloyd, and David will do better than me. So I just want to be honest.
All right. So this is what we're going to be like looking at today.
But they also
There's
make
a
it so really crowded.
so we've already kind of defined again oxidation and reduction in terms of electron transfer and oxidation numbers. We've talked about that a little bit. We're going to be looking at what a galvanic cell is and how it converts chemical energy into electrical energy. Actually, do we all remember what half equations were? Maybe I'll go over the half equations.
I think we should.
I'm going to go over the half equations again.
You just destroyed it.
What?
You broke the white thing.
What?
The white thing, yeah.
The white thing, I took it off?
You just destroyed it.
No, that was already there. No, I put my leg on top of here, by the way. Guys, not that funny.
Broke it when you stepped up.
You released sound energy after you stepped on it. That's how I can tell that you destroyed it. As you
What is he talking about?
When you broke the bonds of the wood, it released that way.
So if we look at the half equations, we want to write the two half equations, and it comes the net ionic equation if we remember, right?
That was so easy.
That wasn't that bad.
So we have two half equations. One's the oxidation, one's the reduction equation, right? So what do we say zinc underwent?
I think like 45
Oxidation, right? So it meant it lost or gained? It lost electrons, right? So what that means is it released electrons, right? So that means electrons should be a product of the reaction, right? We didn't have electrons like lost before, so it must have been released as a product of the reaction. So this is our oxidation half equation, right? And you always balance your number of electrons to the difference in charge, basically, between your initial and your final products, right? Which makes your copper, did it lose or gain? It means it must have gained electrons, right? Which makes your electrons a reactant as opposed to a product, right? Yeah? And so these are two half equations. If you add them up in this case, you should get your net ionic equation, right? Because if you think about it, if you were to try to turn this initial equation from its base equation to its net ionic equation, what you could cancel out is basically only the sulfates, right? Because these two are solid, so you leave them alone. These aqueous, like the next step from going to your net ionic would be like zinc solid plus Cu2 plus.
So this is a quick question, yeah. Like, when you write your net ionic equation,
Mm-hmm.
like, what's your final form of your net ionic equation?
What's my final
You
form?
know how you have like Z, like two equations there?
Yeah.
Involving Z and Cu?
Yeah.
Is that, do you have to write two equations or do you combine them?
Yeah, so these are your half equations, right? Use your half equations to farm your net ionic. So if you add both sides here, what you would get is zinc solid plus Cu2 plus aqueous plus 2E minus. And then on the right hand side, you would get zinc 2 plus aqueous plus 2E minus plus CuS, right? So from your two half equations, if you add them, you can cancel your electrons, right? Because they're common on both sides. You'll get this as your final net ionic equation. Similarly, if you go to the normal process of writing your net ionic equation, you'll get the same thing, right? So two ways of getting to your net ionic equation in redox context.
You could either do that or you could do half equations.
Yep. Does that make sense to everybody? But in this case, because the electrons are like nicely balanced, you don't have to balance and do any sort of simultaneous. There's no ideas of doing simultaneous. But for example, if it was like hypothetically like zinc 1 plus, you would have one electron here, and you'd have to multiply 2 to balance the electrons so you could cancel
So
it.
the E is coming from the sulfate.
The electrons.
The like the random E of the end.
These electrons are the electrons being transferred, right? Yeah.
So okay. So what if it was Cu and it was like something that some sort of anion that's 3 minus? What would you do then?
If it was some sort of anion
Like, some sort of polyatomic ion that was 3 minus.
here.
Yeah, let's say it was 3 minus. Let's just say it was sulfate 3 minus.
But that wouldn't
Okay, so if it was
react.
somehow 3 minus here,
Yeah, what would you do?
in terms of like these equations,
Would you still do 2E minus? Would you do 3E minus? Like,
so it depends on like what's being oxidized and reduced, right? So let's say if it was SO4 3 minus hypothetically, right? Then this would have been Cu3 plus and zinc 3 plus. So it would,
you would have just changed to 3.
yeah, these would have just changed to 3, yeah? because you're only focusing on basically the changes in the electrons of the like the two species undergoing oxidation reduction, right? Does that make sense to everyone in terms of half equations and that sort of stuff? Yeah. Okay. Cool. Waiting.
Writing all that down. Yeah. Every single box.
You're writing the boxes down.
Oh, no, I'm just writing down the final equation.
Yeah. Nice. All right.
How was your holiday, sir? What did you do?
What did I do in the holidays?
Yeah.
Well, my holiday is actually over today. So I'm going back to uni tomorrow as well. In my holidays, I went to the Gold Coast, saw a couple friends up there. I don't know, like, I started reading again. Yeah.
So why? Okay. So the electrons went from the zinc to the copper.
Sorry.
So the electrons on the left-hand side of the equation.
Yep.
Because there's a 2e minus on both sides. The 2e minus can go anywhere. Right?
Sorry. The
2e minus.
the 2e minus. Okay. Sure.
Both sides of the equation. It doesn't go anywhere.
The 2e minus doesn't go anywhere. They're just like. What do you mean by doesn't go
They
anywhere?
just float around. Like, what's the point of including them in the equation if they don't actually do anything?
In your half equations.
In the final equation, or do you not?
No, you don't include them in the final equation. Okay. Any other questions from that? No. Okay. Actually, before we go into the slide, look at the next page on your booklets. If you look at
Sorry, just quickly, what's it called again? The equation,
the net ionic equation. Okay. Yeah, so if you look at page 4, there's a prompt here. It says compare the similarity and differences between setup B and setup C when a metal conductor is connected with zinc and copper rods in terms of observations and reaction equations. So, what we're going to look at here is if you look at literally the difference between B and C is that there's something conducting between the two,
what's B?
in your book. On page 4. Yeah. There's something conducting between the two solutions, right? Oh, sorry, the two metals, right? So what do we think the difference is going to be here? Yep. So there's no difference except there's a wire.
The charge would have to be the same.
Sorry?
Which one of it is?
The charge would have to be the same.
What is this diagram? What is this diagram showing?
What is this diagram showing?
Yeah.
So it's showing a zinc block and a copper block in a copper 2 sulfate solution.
Okay, and what are we supposed to see?
What are we supposed to see?
Yeah.
So what should okay? Let's say you for setup B, right? Let's say you take hypothetically were to take the copper out of the solution. What would happen?
I think the zinc, the top of the zinc, would get covered in copper.
Yep.
So the copper would, no, the zinc would displace the copper.
Zinc would displace the copper.
Yeah.
Yeah, that's typically what should happen, right? So in setup B, what happens is that there's a direct transfer, right? So zinc dissolves directly into solution, right? So what happens is the electrons that are dissolved so when zinc goes into solution, again you have zinc into zinc 2 plus 2e minus, right? These electrons are transferred to the copper in solution, right? This is the oxidation, this is the reduction. The electrons that are used are created in the oxidation, basically drive the reduction, right? So then this is what's happening in the solution, right? So what happens is the copper metal will then deposit on the zinc surface, like you said, right? Importantly, it only happens at a local surface, right? So it's exclusively at the zinc metal block, right? In setup C, the most important like difference is that like the chemistry here is the same, right? It is still the reduction, still the oxidation happening, right? But like the idea here now is that because like you have zinc and you have copper, right? The electrons are able to take the path through the conductor to the copper, right? And then from that, it drives an electrical current. And the main important like focus here is that that current is you've changed chemical potential energy into electrical energy.
Okay, and then so what does that mean?
So the whole like I guess the purpose of what we're looking at today is a galvanic cell, and this is like the basic setup of a galvanic cell. It's the so it's if you look at this setup here, it's basically this setup here, except if you turn the page over, you kind of have like two separate containers. It looks really complicated, right? But this idea is like what we've been talking about so far. So if we look at the next like slide, right? Oh, sorry, the next like page, right? You'll see that you have this. Actually, I'll draw it. Might be a bit easier to see. So you have like this setup here. It's basically like you have two containers. You have one of your metals. You have your other metal. You have something connecting them. Right? This is the general setup, right? And so before we get into the actual parts of the galvanic cell, the general gist here is that you have, let's say in this case, zinc, and you have copper, right? You have the you have the solutions, and what happens is because of these ideas of reduction and oxidation, you drive electrons to, because again, before when the setups were just like when they were in the same solution, right? The reduction and oxidation process happens at a local site, right? Because it has to come in contact with the solution, right? What happens now is that because they've been separated now, right? Right? What happens is the electrons must travel through this circuit to get to the next solution, right? Because if you generate like electrons, where's it going to go? Because it's in a zinc like
So
solution.
the copper needs the electrons, but the copper isn't on the
Yeah, so it drives an electrical current, and that's how it converts chemical potential energy to electrical energy. Yeah? Does that make sense?
Yeah. So that's what a galvanic cell.
That's basically that's the principle of a galvanic cell. So yeah, in setup, oh, it didn't turn back on.
So what is the can you just give a definition of galvanic cell?
Can I give a definition of a galvanic cell?
Yeah, just like if I had to remember something. If
Um,
I had to like remember something to remember.
I would say it's basically just. Actually, I'll tell you the definition after I get into the parts of a galvanic cell because it'll become a bit more clear.
So the half reaction, that's a half reaction.
These are the two half reactions, right?
Okay.
This one's happening in one cell, the other's happening in the other one. Does that make sense?
Instead of the text to write half like equations or something.
Yep.
I didn't know what that was. I didn't know what it was.
Here's your opportunity to.
Yep. So
No, but
so yeah.
I
So in setup, see, it's the same chemical reactions, but oxidation and reduction occur at different locations, which forces chemical current or electrical current through the wires. Yeah, or the wire. Okay. So yeah, our galvanic cell uses redox reactions to generate electricity by forcing electrons through an external circuit, right? So you'll notice that we have in this setup we have two like metal blocks, right? One of them is called the anode and one of them is called the cathode, right? So the more reactive metal is called the anode, right? So more reactive is called the anode, and at the anode, so in this case zinc was more reactive, right? What process occurred at here? Yes.
I just got another question.
Yeah.
Does galvanic cell only work if the solution that the metals are in comprises of the less reactive metal?
Does the galvanic cell
Only work if the solution that the metals are in comprises of an acid with the less reactive metal? You know how copper is like less reactive
Yeah.
than zinc?
Yeah.
If it was a zinc solution rather than a copper solution, would this still work?
if it started as zinc solution, there would be no, you wouldn't like start the like oxidation. Yeah. But like importantly, like yeah, so like you would have wait, say that again.
Yeah, I think I
Okay, cool. But importantly, if we look at the galvanic cell, right, we have again two one of them is what we call the anode, one of them is what we call the cathode, right? So zinc was our more reactive metal, so does it undergo oxidation or reduction? Oxidation, right? So the anode, oxidation always occurs at the anode and the opposite, so reduction occurs at the cathode. So things like anode, first of all is oxidation, and it's more reactive, right? Cathode is reduction, and it's less reactive, right? And the reason why this definition is because electrons come out of the anode and then go to the cathode, basically, right? So you have to have the same sort of like principle of electron liberation, and then so it can travel around and like form the like circuit, right? So yeah, in this case, like your zinc is your anode, and then your copper is your cathode, right? Does that make sense to everyone? And then associated oxidation and reduction. So you also have the external wire, which is obviously needs like a conductive material so your electrons can pass through it, right? And they travel again from the anode to the cathode. And that's the electrical current that we're talking about in terms of changing chemical to electrical energy. And importantly, what we have is like a salt bridge. So a salt bridge is something that like sits in between the two solutions like this. It basically like almost connects the two solutions. But the point is that what do you think happens as you like, if you didn't have this salt bridge, what do you think would happen as you kept leaving this running? Mm-hmm.
The zinc would displace the copper in solution.
Yep.
Right.
The zinc would displace copper in the solution, sure.
And then the copper, what would happen to the copper? The copper would turn from solution to, no, the zinc wouldn't, yes, it would.
So again, the whole point of what's happening here is that you have electron migration from like anode to cathode, right? Initially, it's just driven strictly by like your oxidation, right? So it just shoves the electrons out basically, right? So what happens, what do you think happens? Like let's say like initially, right, you should have no net charge in both beakers.
Yep.
What happens after you leave it running for 10 minutes, for example?
The anode becomes very negative.
The anode becomes very negative.
Anode becomes very positive.
Yeah.
The cathode becomes very negative.
Exactly, right? You have your anode becoming very, very negative because you keep losing electrons. Oh, sorry, your anode becomes positive because you keep losing electrons, right? And you get a buildup of positive charge in your cathode, right? Because your electrons are running all the way around here, right? So your electron is like moving like this, right? So you get a buildup of electrons in your cathode, right? At a certain point, what happens if you have too much of negative charge in your cathode? It's going to repel the electrons from coming, right? It's going to stop the current from flowing. So you need this salt bridge, which typically consists of like basically like normally it's like KNO3, something like this, right? And basically this KNO3, it distributes to neutralize both solutions. Like basically one side, the positive, the cation will like help neutralize the negative side, and then the anion will help like neutralize the positive side. So it balances the charge and keeps driving the current. Does that make sense? Because otherwise, if you get too much of a build up of negative charge here, your electrons are going to stop flowing, right? Because it's going to repel. Yeah, so you need to neutralize that such that your current keeps flowing. Does that sort of make sense?
So where's the salt bridge in this example?
So not in this one. If you flip to the next page, you can see that there's that thing in the middle, right?
Oh, that's the salt bridge.
Yeah, that's a salt bridge.
Is it salted?
Yeah.
Fully salted?
Well, it's like,
Salted.
it can't really be liquid.
Choice.
So yeah, does that make sense to everybody?
Just, yeah.
Yep. Anybody have any questions up to this point?
Wait, why does it start like repelling the?
Because if you let's say you have two like magnets, right? If you have the same ends, right, they'll repel, right? So you're continually getting electron transfer from one beaker to the other, right? So let's say these both start with a charge of like 0, for example, right? What happens after you let's say you lose one electron every time. After 10 cycles of this happening, this is going to become plus 10 because you've lost 10 electrons. Here, you're going to have minus 10 because you've gained 10 electrons, right? If this is negative 10, this you can think of the beacon now as like a charged object. If you have a negatively charged object, another negatively charged object, being the electron, is going to get repelled by this negative charge. Does that make sense? So it's going to like stop the current, and that's why we need the salt bridge to sort of like neutralize it out. Yeah?
Can you explain what the salt actually does to neutralize the solution?
What the salt actually does to neutralize the solution. Like, you have like your it's like it's basically just like for example the metal or whatever, the cation is basically just gonna take in the electrons.
In the salt. The metal?
Like it's gonna like, yeah, so basically like one side of the salt bridge, it distributes the cation, one side distributes the anion into the respective beaker, right? And because one of them is positively charged, one of them is negatively charged, it like.
So you're saying the salt dissolves into the. Wait, I don't get it.
The salt, like it doesn't really like dissolve, like it just allows like, so you have the bridge, right? It's not necessarily like it basically just think about it as it feeds a cation or an anion into either solution to neutralize the charge on either side. That's basically all it is. It's not, don't think about it as if it's like physically dissolving into it. Like it could even, it doesn't even have to be like for example, an actual, like it doesn't actually have to be composed of like, for example, like KONO3, right? It could literally just be dispensing it. Yeah, does that make sense?
So it could just be putting
Ions in, it could literally just put, like you're just pumping it in, right?
So it puts anions into the. What do you think? So anions are negative. So it puts anions into the anode. What's it called? Anode.
Yeah,
It puts anions into the anode,
Yep.
and it puts cations into the cathode.
to balance, to maintain electron neutrality, right? Because again, this salt bridge is not a means for the two solutions to like sort of like connect, right? It's just the sole purpose of it is just to maintain electron
So
neutrality.
is there any reason for it to be a bridge?
I like, not necessarily, I would say. I don't think, like the term bridge, I guess, leads you to believe that it like connects the two, but yeah, I just call it a salt bridge, I guess. But it's literally, yeah, it's literally just like, just think about it as pumping ions into either solution to maintain electron neutrality. Does that make sense to everybody? Yeah. Okay, so then what you'll see in like these arrangements here is like you have like this thing here, right? What that is it basically just measures the voltage through the circuit, right? Because if you look again at your periodic tables right now, you'll see that on that like standard reduction potentials page, you'll see a bunch of like they're basically half equations, right? And you'll see an associated voltage value, right? Different, like again, because metals inherently are different in terms of like atomic structure, in terms of their like just properties, right? Liberating an electron again has different like quantities associated with it, and one of them is like differences in voltage, right? So liberating an electron from, again, like copper versus zinc is going to be inherently different, right? So what this does is it measures the difference between the oxidation at one end and the reduction at the other end.
How does it do that?
Sorry?
How does it do that?
Because like again, if do you do physics?
Yeah.
So like voltage is like,
Oh, I haven't got that yet.
okay, so but basically voltage is like difference in potential energy, right? So you're measuring like basically, let me think about how to explain
Yeah,
this.
so I get what voltage is.
Yeah, it's basically just measuring the difference on both sides.
So you use the voltmeter.
Yep.
And then it tells you something.
It'll give you a value, right? It'll give you a reading, right? And what it should do is be corresponding to like the values that you'll have on your data sheet, right? So because one of them, if you look at the, like again, the values will be on your data sheet are going to be reduction, right? So one of like, it's going to be corresponding for the reduction side, but you have to flip the oxidation side. I'll tell you, we'll talk about that in a second. But like again, the voltmeter is just to measure like the voltage in this circuit.
So I got a question.
Yep.
If you had the anode, so okay, if you had the cathode
Yep.
being really not reactive, like what's the least reactive node? Like
if you had a
What's the wait? What did we determine as the least reactive metal? Like cesium? Or that's the other way around.
the least reactive metal.
Like you know how like zinc is more reactive than copper.
Yeah.
What would be the least reactive metal?
Something probably like
Top. It would be top left.
so like this is like the reactivity is like affected nuclear charges. It's like
Also top right is.
yeah.
Aluminium.
So
Yeah,
we
sure.
could say if you had aluminium as the cathode and you had like cesium as the anode,
If you had okay.
and cesium's like really like reactive.
Okay.
So like 1T, 1T. Would that mean that the voltmeter would give like a higher reading? Is that what it would mean?
Yeah, because there's a bigger difference in potentials, right? But yeah, we'll talk about that in a second in terms of actually magnitudes and how we work that out. But first of all, does the actual like setup of the galvanic cell make sense? Yes. Okay. All right. So these are again the most, I guess, the important types. Important things to know again: the anode, cathode, electrolytes. I just talking about the solution, I guess, and then the salt bridge, ion migration in terms of just like pumping ions into each external circuit. And then importantly, this part here is like, this is important, right? So this last part here is, you can see that on like the reductions potential sheet, there's also like mention of like non-solids or like non-metals, right? So things like hydrogen or whatever.
Oh, so this the potential. That's what we're learning.
Yeah, that's what we're talking about today.
This
So-
entire page.
Yeah, basically, that's we don't again because it's there for you now, so you don't really have to remember too much. But the idea is this discussion point of platinum, right? So for something like gas, right, you can't really just put the I don't know the conducting the external circuit into the solution, right? You need something solid, right? Why platinum is used to facilitate this is because platinum is really, really unreactive, right? So it's not going to cause any other reactions to occur other than what's intended, if that makes sense.
Whoa, so what's platinum?
So platinum is used like, okay, so normally in our setups we have an anode and a cathode, which is a solid metal surface, right? Because typically we're concerned with just like metal reactions, right? But in the case of, for example, like if you're trying to like, I don't know, part of the experiment is like hydrogen for some reason, right? Hydrogen is a gas, right? You can't really just put the hydrogen in the solution and put the thing in the solution, right? So the idea is you use platinum. It's kind of like, it's like, do you guys know what like, have you guys talked about like catalysts before? Like homogeneous versus heterogeneous? No. Okay. So it's like a catalyst is basically used to basically speed up a reaction, like fundamentally, right? Yeah. So it's basically to provide a surface for reaction to occur, right? That's like the difference between homogeneous and heterogeneous. So homogeneous is basically a catalyst that's the same state as what the reaction is occurring in, right? But a heterogeneous catalyst is different, right? So it's basically like you said, it can be used to provide a surface for reaction. Right? That's kind of what the platinum is doing here. It's providing a surface for the reaction. It's facilitating it, but it's chosen as platinum because platinum is very, very unreactive. So it's not going to influence the reaction in any way.
Okay, so hydrogen
Yeah.
would be like one of the things of
Yeah.
this galvanic cell.
Yeah.
And you would put platinum there so that hydrogen can do its half
Yeah.
reaction.
Yeah, basically. It's basically just used to facilitate the reaction. Yeah. But yes. Okay, cool. Any other questions? Okay, cool. So yeah, this is just a basic recap of everything that we've talked about here. So at the anode, you get oxidation, you get release of electrons, and then you get increase in oxidation number, and then this is the oxidation half equation, for example. This is the reduction half equation that happens at the cathode. But yes. Okay. All right. Yeah. Okay. Yeah, so if you look at like the image on page 8, you'll see what I'm talking about as using like platinum as a like facilitator for the reaction, right? So they basically just pump hydrogen gas into this little tube and then leave it there. Okay, cool. So, yeah, does everyone understand how a galvanic cell basically works? So the main idea is basically, like if you wanted to, again, come back to this definition of a galvanic cell, I would say it's basically just a means or a setup that converts chemical potential energy to electrical energy through the use of oxidation and reduction at an anode and cathode using an external circuit or something like that. That's probably a pretty rough definition of a galvanic cell. Okay, cool. So, if we take a look at the example on for question 10, have a go at that. And don't look at the next page, which has the answers.
So, a question or what?
Question 10. Oh, page 10 on the.
My pen doesn't work anymore, so it's nice.
So in this, like, I guess, question, like, you're looking at these two electrodes, right? So you have a zinc one and you have a platinum one. So in this case, if you look at the zinc one, it's just like a normal piece of zinc metal. The platinum one is in this case facilitating a reaction between an aqueous solution, right? So one of like iron. So iron 3 and iron 2, right? So basically what you want to look at here is you want to identify what process is happening at each electrode. You need to identify first of all, like whether it's oxidation or reduction, and then you have to determine like which way the current will flow, I guess, right? So I'll give you guys a couple of minutes to think about that. You can use the data sheet to help you if you can figure out how to use it to help you. We'll talk about it after, but I want you guys to kind of think about it.
Can you explain the thing about platinum and iron?
Platinum and iron.
Yeah, why is there a platinum wire at the iron electrode?
Why is there platinum? Because in the zinc one, right, you have a piece of zinc metal,
Yep.
right? But in the platinum solution, like the platinum is not what is actually reacting, right? The reaction that's happening in that side is between iron 3 and iron 2, so it's an aqueous solution. So again, the platinum is facilitating that reaction to occur. Platinum is like irrelevant, like the actual platinum itself.
So where is the iron?
Sorry?
Where's the iron?
It's
The
in
iron's
solution.
Okay.
Right.
The iron's in solution, and the solution's made of. What's the solution made of?
The solution has like Fe3 plus, Fe2 plus, and the sulfate.
Okay. Well, okay, so the iron solution, the zinc is also in the iron solution.
The zinc is not in the iron solution. If you look at like the left side solution has zinc. The right side solution has.
Oh, so there's different things in the solution. Doesn't that like defeat the whole?
Sorry.
No. So wait, why does zinc undergo oxidation if the solution that it's sitting in has zinc in it?
If
Wait, what's the zinc block sitting in? What's it sitting in?
so, like you the way that like we set it up before was that it was in like the way that we set it up before was that it was in like the copper solution, whatever. Right? It would undergo oxidation, right? But like the way that this gets set up, like you can see in this setup, it's zinc in the zinc solution and then platinum in the iron solution, right?
Okay. So what causes zinc to undergo oxidation if it's not even sitting in a copper solution?
Because zinc is still going from zinc to.
Like why? I don't understand why.
you don't understand why.
Why would it do that? Like what's the reason for it to do that?
What?
Like it's oxidizing, right?
Yeah.
Zinc is oxidizing.
Yeah.
So why does it want to oxidize?
Why does it want to oxidize?
Yeah. Like what's driving it to oxidize?
Wait. Like why is it going from zinc to zinc 2 plus? Like it's like in okay, I think like in because like okay, I guess the way I explained it before was that it was because it was like in the previous solution it was driven by like it displacing.
Yeah.
Like
Yeah.
okay, like it's like metals when they like I guess when you like for example put I don't know like if you put a zinc bar in a water solution even for example it would still have some like innate like it would still innately still oxidize even if it's not like yeah it's just metals have an inherent property where they like basically dissociate. So it's just like how if you put like a little bit of zinc like metal powder into a bit of water
Yeah.
it might like it'll like dissolve a little bit, right? That's still enough to start, if that makes sense. Like the oxidation procedure, because like when you put like again a little bit of zinc powder into water, right? It'll still like dissolve, like no matter how like minuscule amount actually dissolves, it still dissolves, right? And the dissolution from zinc metal to zinc in solution is an ion, right? Which is still a process of oxidation. Does that make sense?
So it oxidizes.
Yep.
It creates Zn2 plus.
Yep.
As well as 2 electrons.
Yep. And then the electrons.
Go through.
Yep. Okay, I think were you a bit confused because I explained it as like before, as the reduction, as like the other solution facilitating the.
Yeah, I thought it was.
It's due to that.
Yeah, the
Okay.
reason that it was actually oxidizing
Okay.
because the copper.
Yeah.
was in it.
But yeah, it still starts because there's still inherent.
And then once the thing starts,
Yep.
it just keeps oxidizing.
Yeah, because you inherently still have so much zinc in there, if that makes sense, right? Like the zinc's not gonna run out. Yeah. Does anybody else have any questions to clarify? No? Okay, cool. Have we had to think about what's happening in this question?
Yeah, so for part B.
Yep.
What's the form of the answer that it's looking for? Some sort of reaction?
It's looking for like probably the net ionic equation in this question. So you combine the oxidation, because part A directs you to find oxidation and reduction. So from that you can find the half equations. So the overall reaction is the combination of the two half equations, right? Following? I agree. I think galvanic cells, first time learning is pretty challenging. But is there anything in particular you're like it's a bit confusing?
No, nothing in particular.
Just a bit new.
Okay, so Zn plus Cu2 plus
Mm-hmm.
becomes Cu plus Zn2 plus. Is that it?
Sorry.
For part B.
For part B.
Yeah, I'm just a bit confused on part B because the zinc. Oh, wait, sorry, not Cu. It's gonna be Fe, right? Yeah, never mind. Am I gonna have to create 2 reactions? One of them involving Fe3 plus, one of them 2 plus.
So when it says Fe3 plus and Fe2 plus, so it's just like how in your zinc, in the zinc electrode, right? It's the reaction from zinc to zinc 2 plus. In the iron one, it's going from iron 3 plus to iron 2 plus. And that because iron 3 plus and iron 2 plus are they're two ions, right? That's why there's no block. That's why you have platinum to facilitate that reaction, because there's no solid iron in there. Does that make sense? Yeah. Are we following? Any questions? Yeah. Okay. Any questions at the back? No. Makes sense. Kind of.
So Fe3 plus is going. It's it's going from Fe3 plus to Fe2 plus.
It's going from Fe3 plus to Fe2 plus.
And then the net ionic equation is going to involve both Zn plus Fe
The net ionic equation is going to involve both Zn.
and Fe, even
Yep.
though they're not in contact.
Yeah. Because just like how, even though they're not in contact, the amount of electrons being transferred from the zinc to the iron, like the electrons being transferred into the next solution is also like, that's the whole reaction, if that makes sense, right?
Am I going to have to like balance this equation?
You can find out for yourself.
That's my cathode equation. 'Cause that's what's that? That's reduction. Reduction is gain.
Reduction is gain.
Alright, so I have to balance this equation somehow, yeah?
So you balance always based just off of like the electrons, basically.
So can I just add an E to the left-hand side equation? Is that what can I do?
Can you add an E to the
So
left?
right now I've got something with an E minus, and the other side's got a 2E minus.
Yeah.
Do I just write 2 next to the original one?
So the idea is that the electrons, like kind of being used in the second half, come from the first one. So you want to balance the electrons, right? That's what you want to do.
Yeah.
So just like how in simultaneous equations, how would you eliminate something? Like if you had like,
Oh, so wait, do I have to multiply everything by 2? And then I can cancel out the electrons?
Yeah.
Alright, okay. So 2 Zn's is becoming a Zn2 plus, and 2 Fe3 pluses is becoming a Fe2 plus.
say it again?
Yeah, that doesn't make sense. So wait, what sort of, can you write your answer to part B?
Okay, so what's our first equation? What are our two equations, first of all? Let me write this out. We have our zinc and we have our iron, right? So I'll just draw it like very basically. So we have zinc over here. We have iron over here. I'll leave platinum and then iron. And you have zinc in solution. So the zinc side, what's happening?
It's turning into Zn2 plus plus 2 minus. It's no, it's oxidating.
It's oxidizing.
Oxidizing.
Yeah. What's happening at the other side?
It's reducing.
Yep. So if it's reducing, it means it's gaining an electron.
Yep.
Right. So what we do is balance these. So we have 2 electrons here. We have 1 electron here. We need to times the second equation by 2. Yeah. So we get 2 Fe3 plus 2E minus becomes 2 Fe2 plus. Yeah.
So, but if I write the equation above that,
This
as,
one?
no, below that, yeah. If I write that as my half equation, that's still valid.
This.
Yeah.
That is that. Yeah. That would be the half equation.
But then,
To get to your full reaction equation, you have to now add these two, right? And then these two cancel out, so you get Zn plus 2Fe3 plus becomes Zn2 plus 2Fe2 plus. Does that make sense to everybody? Net ionic equation makes sense to everybody? Hopefully that makes sense. Then like solid, aqueous, aqueous. Yeah. Cool. Third part is asking, in which direction do electrons flow in the external circuit? So are do we think it flows from zinc to iron or the other way around? This one should be pretty simple. So is it from zinc to platinum or platinum to zinc? Yeah, right, zinc to platinum. And the last two, in which direction do ions flow within the cell? So this is talking about like the salt bridge. So if we have electrons flowing this way, right? Right?
Get out the other way.
If we have our...
The ion's gonna flow the other way. Right?
So which way are the ions flowing?
The other opposite direction.
So cations are going which way? Cations are going, so let's say C plus is going this way.
Ions going in the same direction as the electrons.
Cations are going which way?
Same direction as the electrons.
Cations are going this way, right?
Yeah.
And then anions are going this way. Yeah? To balance the charges. Cool. And then the last one is which electrode is the anode? Pretty simple. Zinc or platinum?
Wait, which direction is the electrons flowing?
Electrons are flowing from zinc to platinum, right?
Isn't that like, I don't know, but isn't that like something like dodgy about that? Like, they say this, but in actual fact it's like something else. That's what I sort of heard. Like
What?
they say that it moves in that direction, when in real life it moves in another direction. Is that true?
I'm not sure what you're getting at.
Somebody knows what I'm talking about.
Does anyone know what he's talking about?
She knows what I'm talking about.
Yeah, she does not know what he's talking about. Yeah, you might be capping. Yeah, this guy might be schizophrenic. Cool. So then we get zinc is the anode, right? Does that make sense, everyone? Yes. And then you can read the answer. Oh, it doesn't even say the answers for page 12. Yikes. What?
No one heard you.
No, I heard that. I think everyone heard you.
No one.
Okay. The next sort of thing we have to talk about is like the actual you can see it, the actual forces. Also the actual values that we have, right? So the EMF or the electromotive force is basically the voltage that we're looking at right now. Is a potential difference across the electrodes, right? And it's basically the maximum voltage a cell can deliver. Right, so it's basically if everything from the anode went to the cathode, that's the measurement we'd get, right? If there were no issues with conduction or something like that, right? So so we have this set up like this one here is for reference purposes because we need to get these values from somewhere, right? So with reference we use what we call a standard hydrogen electrode. So you can see on your periodic tables, there should be a 0, right? Is there a 0? There's a 0, right? 0.
Yeah, it's hydrogen. Right?
Yeah, it's the hydrogen one, right? Does everyone see it? Like the 0.0. It's like the the 0.0 volts, right? It's the hydrogen one, right? That's basically our reference point, right? So everything is measured relative to hydrogen. Yeah. So if we look at what the EMF tells us, it's always written as a reduction potential. So if we look on either side, you'll see positive and negative values, right? So what this tells us is that a positive E, so that's on the bottom side, is a strong oxidizing agent, and then a negative one is a strong reducing agent. So just take a bit of a read. Yeah.
What's E?
The electromotive force. So it's basically if the entire experiment goes correctly, if there's no issues with conductivity, if there's no issues with our solutions, if there's no issues with anything, it's the maximum voltage a cell can deliver. So it's basically the maximum current across.
Voltage of force.
Hmm?
Is voltage of force.
Voltage is not a force.
Wow. So what's it called electromotive force?
Presumably because it's like the electrostatic force that drives the electrons around. But
So the E is this number that I'm seeing here.
yeah.
That's the electromotive force.
Yeah.
Okay, and
Or E is like this, no, E is actually the number that you see there. Electromotive force is the difference across two electrodes. So that is the electromotive force when compared to a hydrogen electrode. Yeah.
So can you use these numbers to compare any two things?
So then so positive means that it readily accepts electrons and is a strong oxidizing agent.
So E is a reduction potential, but
Yep.
if it has a positive E, then it's an oxidizing agent.
Yep.
Oh, because it has so if If it has
If-
a positive E, it's
it-
going to reduce, which means it's an oxidized reaction.
So, yeah. So like, again, all of these are with reference to your your hydrogen electrode, right? So, like hopefully that just like makes sense that it's a standard, right? But then we can also use it obviously to compare, like, the others, right? So if we look at like page, like if you go to like page 16 now, you can see that the way we calculate like the EMF and the way we compare is we add the EMFs of the reductant, or the species undergoing reduction and the species undergoing oxidation, right? So the way that like you can like see this is it's like the if you just look at the example that they give us, right? So it's using nickel and chlorine. So let's find those two on the the data sheet. And if you look at it, you have nickel going to Ni2 plus 2E minus, and you have chlorine plus 2E minus to 2Cl minus, right? Those are the two half equations that they give us.
So chlorine is 1.4. Nickel is negative 0.24.
Yeah, so those are the two values that you actually get, right? So which one in this case is undergoing reduction, which one's going oxidation? Sorry?
Chlorine is undergoing reduction.
Yeah, so like if you, yeah, so like, does that, so chlorine's value is, what was it again? Tell me. Yeah, 1.4, and then what was,
Negative 0.24.
so which one's the better at like undergoing?
Reduction, chlorine.
Okay.
Oxidation, nickel.
Okay, so importantly here, when it's called reduction potentials, right? It like assumes that the reaction, because it's relative to the hydrogen electrode, all of your values are assuming it's undergoing reduction, right? Does that make sense? So, yeah, it's assuming it's undergoing reduction, right? Which means that when you add these two together, one of them's undergoing reduction, one of them's undergoing oxidation. So what does that mean to the one undergoing oxidation? So all of these values for E assume that the species is undergoing reduction.
Okay.
Yes? But when we compare two species, because these like numbers are made like again, assuming relative to the standard hydrogen electrode, it's undergoing reduction.
So if it's negative, that means it's not undergoing reduction.
If it's negative, that means not under.
Yeah. If it's negative, it means it's undergoing oxidation.
Okay, sure, yeah. Which means that,
Yeah.
but what I'm getting at is basically like, because again, all these values are assuming reduction. So it's assuming electron transfer in one direction, basically, right? When we consider, for example, now nickel and chlorine, we're comparing like one of them's undergoing reduction, one of them's undergoing oxidation, right? So obviously the one undergoing oxidation, its number is like, yeah, that's basically what I'm getting at, right? Because it's going in the other direction, right? So you'll see that the formula here is like, you know, EMF is equal to like reduction plus oxidation. A lot easier is like the EMF is equal to the E right? Because the anode is undergoing oxidation. Does that make sense to everyone? So instead of adding like the reduction and the oxidation, you can just subtract based on which one you know is at which electrode. Does that make sense to everyone? This is what? Yeah. But yeah. Okay. So yeah, if you want to like very quickly flip to the next page and try the example, but like cover all the text except for the first line because it tells you the answer. Or you can read the answer if you'd like.
Cover all the text
Except for the first line. He's already read.
Kind of virus positive.
Huh?
What?
Page 17.
Not on the right
He's,
page.
he's a bit far behind.
Calculate the EMF of the cell made by connecting the CU electrode to a. I was like, well, it's like Oh, calculate the the electromotive force. Oh, this is pretty easy.
Oh, okay.
You just look at which one's negative, which one's positive. You have them up first.
This guy might be a genius.
Well, you said it, not me.
Tough crowd.
24, which year?
49.
Well, you use that 1 1 2.
Yeah.
Multiple choice. Multiple choice
What's the
always
like a multiple choice?
tough.
I lost the marking question too.
Two?
It was like what's
Oh,
the?
yeah.
It was like
That was pretty bad. They gave him they gave us like a complex number,
Yeah.
and they're like the imaginary of
it's like
something.
it was like
Yeah.
So you
what's
just put
the
it in your
imaginary
calculator.
Yeah.
part of like 1/3 plus I or something like that.
Yeah.
It's like what's the imaginary part of that?
And you got it wrong.
And I got it wrong. I still don't know how I've done that. I don't know how I managed to do that.
I'd be
You
pretty
just put
upset.
it in your calculator. It just tells you.
Yeah.
I think I probably messed something up with the negatives. Probably just read this number and forgot about the negatives.
Yep.
Question 2.
Yeah, I would be pretty annoyed with myself.
He got full marks in the entire test, and I couldn't even get question 2 right.
Yep.
Did you get 9 multiple choice, or did you use another one?
I lost one of them on question. It was something to do with which one cannot be K, and it's like these are 3 non-covalent numbers.
Negative 1.
No, but I did the question again, and I still got the same answer. So like I'm just wrong.
Negative 1 is the midpoint. All the
Yeah, I
other
know.
points
I
are the
understand
midpoint.
that, but I understand that. But how do you just find that? How do you just see that?
You look at the 2 points, and then you realize that the y and the z value is just the midpoint. So you just find the point of k.
Yeah,
that is
okay,
the
but what
midpoint,
happens
and
if it's
you say
not?
that z is
What happens if it's not? What happens if it's some random?
It's always in a whole number ratio. They're not going to give you some decimal point ratio. That's
No,
always in a whole number
what if
ratio.
it's like 1 to like 2 to 5? What gets 2 to
Yeah.
5?
So it's 2 to 5, and then you get the
So, but how do you just? But what if it's okay? That's given that's in between 2 points. What if it's not in between 2 points? That doesn't make
get
any
the
sense.
ratio.
Because it's in between. It's now this one's in between them.
Yeah.
I don't know. I did the calculations and I got. K.
Is everyone done?
I don't actually know how to calculate. I don't even know like what working on.
I did the calculation. I got K equals -5, and I was like, oh yeah, okay, like that worked out great. You know when you get it, like when you do some random working and you get one of the answers, it's like, oh yeah, I did something.
That means
right.
you've fallen for a trick they wanted you to fall for.
I fell for the instructor.
That's exactly what that means.
How you would do working out for that question?
No, if I get it,
I
yeah.
said this
Anyways,
one is the-
yeah. So let's look at copper and Fe. So if you look at copper, what happens with copper? What's the reaction? Oh, that's written on the sheet that I don't have in front of me.
And I lost 3 marks.
What's the EMF value of the copper reduction?
And then for you was like.
Uh,
It was too easy for you. Let's just put it that way. You only you got 50.
So you have this as one of the half equations, and you have this as the other half equation, right?
Why is David into math? It's a math parent.
Yeah, I don't know.
Oh, sorry.
I think you should be in this math game.
Yeah, I want to know what Chris was
Like,
like.
oh, sorry.
I don't care.
Apparently
These are 2 half equations for the reaction, right? So with the way we know this is that like we look at the 2 reduction we look at the reduction potentials, right? So copper, what's the reduction potential value?
0.34.
And what's the one for what the heck? What the heck? What's the one for iron?
You don't have English on Thursdays.
What does the iron one actually say on the? If you just read out the iron like on the sheet, yeah. Yeah, and what's the associated E? Yeah, right. So what you'll notice is that this is the opposite way around to the other one, right? The reason I flipped it around here is because you have like this one here, right? So this one here is high, which means that it's undergoing reduction. That means this one's undergoing oxidation. Cathode, anode, 0.34 minus negative 0.44. That's how you get to your final solution. Does that make sense? So for this reaction here, which the way I've written it, it would be 0.44. If I wrote it as it was on the periodic table or the data sheet, it would be negative 0.44 because the reaction is reversed. Does that sort of make sense? Yep, so Daniel's confused. So let's look at what's written on the actual sheet is this, right? when we consider the chemicals that we're looking at, we have this, and then you have
I get it. Okay, it's written as if it's doing
reduction.
as if it's doing reduction because reduction is gaining. It's written that way.
But we know that this is a greater has better reduction potential, has higher reduction potential, right? That means this one's going to undergo reduction when compared to iron, which means that this one's undergoing oxidation. So you have to flip it around if you want to because the formula is like EMF is equal to reduction plus oxidation or whatever, right? So you could do EMF is equal to reduction plus oxidation. To get to oxidation, you have to flip this one around anyway, right? Because this one is the reduction. Flip it around to get oxidation. Does that make sense, everybody? Yeah? You guys in front, good? Make sense? Cool. All right, so we have a bunch of examples. Question 18. Yeah. Have fun with these questions. How did you guys find, the guys who did the exam, how did you guys find the exam? Was it all right? Was it hard? Was it all right? Hard? Yeah. Okay. Yeah. Did I? I marked them all. I was from question 1. I got a bit sad. I was a bit sad after question 1. I thought it was going straight downhill. I thought it was gonna be over. No, after question, I saw question 1. I was like, no way. I was like, yikes, yikes. All right, give the questions on page 18 a go, please, guys. Please. Does anybody still have any questions with anything to do with galvanic cells right now, theory-wise? No. Huh? Sorry? Yeah, you put in the calculator. I had to put in the calculator myself because I was like, this looks really correct. Yeah, happens. And the redox question was a bit rough. The redox one with iron on the previous page. That question was a bit hard. I'm just saying, in general, it was a bit hard.
Oh, those it was rough for me. I was
No, just in general. Yeah. What else did you lose marks on? I forgot.
Because when I was
There you go.
What did you get in the test?
100%.
Net ionic.
Yeah, I saw that. I was like,
Yeah. Yeah, that one was a bit hard. And then,
You could have just copied every single one.
yeah. Yeah, question 1. Question 1. Yeah. I was really shocked. But I think a lot of people got question 1 wrong. I marked 60.
maybe I'm in the majority.
Yeah.
I've got to see this.
It's really, it's not a super difficult question, I would
I
say.
don't know what an oxidation state is, so I'm wrong as well.
Oh my days.
Yeah, her paper got sent to Eastwood. It got banished to Eastwood for some reason.
If I see this as question 1, if I did the test and I saw this question 1, then you
I got the first 2 questions. I got all the last ones right.
Yeah, I was like, I thought after the first 10 questions it was looking grim.
Oh my goodness, what the
He went on a streak. Yeah.
You're like wrong, yes, wrong, yes, wrong, yes.
Yeah, but I feel like a lot of people got question. I was parking the test, and it was not a very high rate of people who question 1 right.
What the hell is an oxidation state?
Yeah, okay.
The laws, you wouldn't even actually remember. Test was really annoying.
Yeah, you're right. Really annoying test. But there were a lot of calculations in this test.
So what's the answer to question 1?
I don't remember question 1. I'll tell you right now. It says C.
What's an oxidation state?
It's basically okay. So, do you remember? Did you watch were you here for the second one?
Oh, I wasn't.
Okay, it's basic.
I'm dedicated.
So basically, right, you know how the simplest way I can put it for you in terms of how to get it right in your exams is basically, right, so neutral substances are neutral, right? Just, yeah, they have no like electrons sticking around, they have no loose electrons or anything like that, right? So you just basically have to figure out. So the question's asking, what's the oxidation state of what is it? Sulfur or something?
Selenium.
Selenium, sure, right.
SeO321.
So SeO3,
2 minus.
2 minus, right? So first of all, you want to isolate the charge of the molecule, 2 minus.
So SE2 plus.
Sorry,
SE2 plus.
Se. If you look at O3, oxygen is 2 minus.
Oxygen or O3?
Oxygen itself is 2 minus. So 3 of them.
I forgot how that was how it worked.
3 of them is 6 minus, but what?
It's basically to do with. Sorry.
Isn't the whole molecule 2 minus?
Yeah. So if it basically again it has to do with electron transfer.
SeSO4 plus to make up. So wait, are you saying oxygen? Oh, like oxygen as in the periodic table is 2 minus.
Yeah. So the general rule is, the oxidation numbers
Okay.
are like yeah.
So the oxidation, so it's basically saying what's the charge?
Yeah. It's basically what's the charge. That's a very simple way of putting
So
it.
an oxidation state is a charge when it's but only when it's in a ionic bond.
Sorry.
Is that what it is?
Sorry.
So what's an oxidation state?
It's basically like the simplest way to put it is basically how far it is from oxidation. So, like,
Oxidation is loss. How far it is from oxidation.
yeah. That's how I always like. It's like the definition is like the definition itself is really like complex. You want me to read? I can read you the definition, but it won't make sense to you, right? Oxidation state is a theoretical integer value representing the total number of electrons an atom has gained or lost, assuming all its bonds are 100% ionic. So it's basically, what does it take to get to to the charge of its ion? That's how I would remember it.
And what's the charge of selenium ion? It is 2 minus. So it takes nothing to get to 2 minus. It already is at no.
What?
It's at 4 plus right now, so to get to 2 minus it would have to do 6 minus.
So like you're always considering it in the context that it is, like it's given to you. So you basically your idea is to assume everything but what is asked. Like, so like it's part of like another like compound. It's part of a compound, part of a molecule, right? You basically, you basically just assume everything except what you're trying to find. So it's like before oxygen, right?
Yeah, so you assume oxygen's O2,
2 minus. Yep.
but you don't assume
You
selenium.
don't assume selenium.
And then
Because
you find-
different ions can exhibit different oxidation states depending on what molecule they're in. So selenium can exist in various different forms. That's why you can't assume what it is, right? Because depending on what it's being bonded to and what it surrounds itself with, it'll exhibit different properties.
Yep.
So you basically, the idea is, look at the charge of the molecule. If it's neutral, you're trying to get to 0. If it's charged, that's the charge you're trying to get to, right? Solids always have an oxidation state of 0, right? Hydrogen is always 1, oxygen is basically always 2 minus. And everything else, like metal ions, is basically always the charge of its ion. Non-metals is basically always a charge of its, like, anion.
So once I find selenium, like what it has to be in order for the ion to fit,
Yeah.
like why is that the oxidation state? Is that not just what it is naturally?
Because selenium can exist in a bunch of different oxidation states. It's just that in this situation, it exists as 4+, for example.
Okay, so it exists in 4 plus, right?
Yep.
So what does that have to do with it reaching reduction or oxidation, whatever you say? Like it existing in 4 plus,
Yeah.
what does it existing in 4 plus have to do with it reaching oxidation or something like that?
Like, because, like in this case, it's to do with, like, so maybe not like reach, like it's kind of the idea of reaching oxidation. So the idea of oxidation reduction again is electron transfer, right? Oxidation state is just like, it's basically just a measure of like, so in this state, 4+, it basically means that it's like, so like selenium being, or so for example, something being like 1+ or whatever, right? Means that it's what? It's like it's lost an electron, right? Which means that, so losing an electron is like, it's oxidation. Yeah, right? So something being 1 plus means that it's like
Maybe that's why your papers are easy.
but it basically is just like
It's undergone oxidation.
yeah, like 1, right? It's 1 electron, right? So selenium being 4 plus means it's going to like in the compound it's going to lose 4 electrons.
Yeah.
That's what it basically means.
So the oxidation state
Yeah.
is how many electrons it has to lose.
Basically to like it's like a I would say it's like a difficult concept to like, but it just for purposes of exams, just like remember it as like charge basically. It's basically just charge, right? Because again, charge fundamentally comes from electron transfer, right? Okay, so we've done the questions in push page 18, guys. I'm gonna pretend we have. So let's have a look at some of the examples. So it's asking us to draw the following cells. So let's just do the first couple. So zinc and magnesium. If you look at zinc and magnesium on the standard potentials, which one's the better? Which one's going to go undergo oxidation? Which one's going to go undergo reduction? Which one has a larger or a small, like a more negative EMF? Okay, so magnesium is more negative, which means that it's going to what? Undergo oxidation. So zinc is, if magnesium is more negative, so it has a larger negative value, right? Does that mean it's better? So if you remember, a negative E minus means a stronger reducing agent and a positive E minus means a stronger oxidizing agent. So it means that, yeah, like you said, we're going to have the process of like oxidation occurring. So what's the half equations that we like concerned with here? I don't think we need the board right now. So for magnesium, what's it undergoing, and what's zinc undergoing? What are our two half equations? Does it have the answers in here? Oh, it does. Yikes. So which one's undergoing? Like we just said that magnesium is undergoing oxidation, right? So oxidation is loss, which means that it's going from Mg to Mg2 plus 2E minus, right? And zinc, that means it's gaining its 2 electrons, which means zinc 2 plus 2E minus going to zinc solid. Does that make sense to everyone? So we have oxidation and then reduction. Yeah? Cool. So that means this one is undergoing oxidation, which means is this the anode or the cathode? Does oxidation happen at the anode or the cathode? Anode. So this is the cathode. And then so it shows electron and current flow. So electrons are going to be flowing from like anode to cathode. And then so it means that cations are flowing which way? Cations are flowing to the cathode because the electrons are going to the cathode as well. So your anions are going to go to your anode. And then to calculate EMF, it's basically, how do we do it? EMF cathode minus EMF anode. Or it's EMF oxidation plus reduction. So what's the value for zinc?
2D.
Sorry?
2D.
2D.
Is question 2D?
It's question 2D. Yeah, question 2D. It has all the answers there actually. So what's the value for zinc?
Question 2 as well.
This is 0. This one was 2 point. So then how do we calculate? We do this one minus that one. So we will overall get, also like cathode and anode, we can just like, we have to flip one of them, right? Wait, so these are the reduction? Or did you say this is what's written? Or is it flipped already? Okay. So which means that this one has to get flipped, right? And then it's cathode minus anode. Yeah. This is, wait, this, let me just look at it. Sorry. It's confusing. Okay, so we have either, so you can, again, it's either reduction plus oxidation, or it's What's the other one? Yeah. So with these two options, if we look at like what's written here, again, this is the reduction potentials, right? So because it's the reduction potentials, let's just say we have the reduction potentials. For cathode, like for the reduction plus oxidation, we can just like, if you look at it for this one, it's zinc is, like you said, oh, it's negative 0.76. And this is negative 2.36. So you can do reduction plus oxidation, which is you have to flip this one. Because this is already reduction, flip the oxidation one, right? Because this is reduction. So you add this, and you get around 1.6 around, yeah. Yeah. So you get like negative 0.76, like mine.
If I beat everybody by like 10 marks, I can probably.
Yeah. Or you can do the other way around, which is
I just want to imagine a scenario where
so this is cathode minus anode.
we'll get like 30 in the test.
If you can think about it the other way, it's reduction plus. It's the same thing. Like you just flip it, but like, yeah. Okay, cool. Sorry, I thought you said 0.76. I was like, oh, that doesn't sound right. That's my bad. Does that make sense, everyone? And then if we look at the next one, for example, silver and lead, which one is the better? Is going to go undergo reduction? Silver and lead.
Oh, let's read the thing.
Yeah, let's read. That would be a good idea.
AG plus
Yeah, that is silver.
0.8 V.
So what's the equation written there?
AG plus E minus.
AG plus E becomes
He was AG.
yeah, right. And what's the 0.8?
PB is negative 0.13.
And what's written there? PB.
B2 plus 2 E minus.
Right. So out of these two, which one's going to undergo reduction and which one's going to undergo oxidation?
Well, very clearly, silver will be the one undergoing reduction.
Do we all agree with that statement?
Yes, because the more negative, yeah.
More negative.
No, the one that's like less goes on oxidization.
The one that's less.
One is oxidization, the positive one is reduction.
Yeah.
So this whole setup is assuming that it's undergoing reduction.
But is
Yeah, thank you.
negative or positive, or just like which one's higher or lower?
So
Negative, positive.
yeah, negative positive is relevant.
The higher or lower doesn't matter. They're both
Yeah. So this one's going to undergo reduction. This one's undergo oxidation, right? So we have to flip the equation for this one to calculate EMF, for example. So we get 0.80 minus 0.13, or we get 0.93, for example, right? And then again, this would be our reduction is cathode, anode. So it means that anions are flowing this way, cations are flowing this way. Makes sense to everybody? Yes. And then for the half equations, what you'd have to do, flip it around, add them together if you want to add the full reaction equation times this 1 by 2, and then add them together, cancel out the electrons. Cool. Makes sense, right?
Can you explain the ion flow? Because they keep saying ion flow, which is making
Ion flow just is referring to the flow of ions in the Soul bridge.
so something is functioning.
Yeah, the ions are flowing.
Something. So the ions are flowing. But what does that mean?
It just means the ions being pumped into the solution effectively.
Do the salt bridge, the electrons.
Yeah.
They go like that.
Yeah, the electrons don't move in the Soul bridge. Electrons are only moving in the external circuit. Yeah, the Soul bridge is just pumping individual ions to maintain electron neutrality.
You know what? Let me put it into terms that you understand. The electrons flow through the wire. However, they keep flowing in one direction, which means they eventually pull up in the cathode, which means the cathode becomes very negative. When the cathode becomes negative, the electrons no longer want to flow there because it's repelling. Yeah, repelling. So to
Okay.
balance that out,
So if we look at the last part of today, importantly, oh, I turned it off.
that's the thing that I don't understand. We keep saying ion flow, which means something is flowing.
Yes, like
Okay, for EMF,
Yeah.
if we have to like multiply AG plus E minus by 2, right?
Oh, that's actually a good point. Yeah.
It's a solve, like positive and negative ions. So the negative
Wait, actually,
positive signs.
no, you don't. Sorry, you don't. Like you don't. Like because it's just like
Any ionic
because
bond value.
it's a potential difference, right? So it kind of like it's kind of just fixed for the ratio in which it happens, right? Because if you add 2 on either side, then of course the ratio will double, if that makes sense, right? But it's a kind of like just a set ratio between the two. If yeah, that's like the simplest terms I can put it in, right? Sorry. But yeah. Okay, the last point I guess that's important to say is about spontaneity. So again, when we hear the term spontaneity, it's about like, does it just happen naturally? Kind of like, if you leave it there, will it happen, right? And so a voltaic cell will always run in, or like a galvanic cell, will always run in the direction that gives a positive cell value.
Yeah, now that you say it, you don't have any clue.
Right? So does anyone want to like try and like guess why this is? Or anyone haven't explained why this is?
Well, everything's usually in October, and the latest ones are at the start of November. That's usually like science is usually math is 30, English is early, and then science is usually late.
Does anyone want to give a suggestion as to why this is the case?
Why it's fun thinking about this next coming test.
So if we think about it, right? EMF is again a difference in
And
like
it's the trial
potential,
this time.
right? So how you can sort of think about this is like a positive EMF value means that the electrons, like, they naturally want to flow from anode to cathode, right? Because you're comparing like the, I guess you're comparing because it's a potential difference, right? If we again, EMF is comparing from like if you think about the difference, right? EMF was what, cathode minus anode. So a positive value means that the cathode is kind of like more positive than the anode. Does that make sense? And electrons will be driven towards the positive pole, right? Which is the cathode in this case. Does that make sense? The way I think about it is like EMF, one of it was like E minus anode, right? So if this is greater than 0, what that means is that like basically the cathode is more positive than the anode. If that kind of makes sense, right? Which means that there is a driving force for the electrons to go towards the cathode because like they're attracted to the positive side, if that makes sense. Does that sort of make sense? So like the cathode, like okay, so this being greater than 0 means that it's spontaneous, right? The reason is because the way I sort of think about it is that if it's positive, it basically means that the cathode is like the way I think about it is like, because this means that the potential of the cathode is greater than that of the anode, right? That's like what this expression being greater than 0 means, right? Does that make sense? Yes. So because EMF like, it represents a difference in like kind of like if it's representing a difference in potential, it's kind of representing a difference in like electron almost pressure at the two electrodes. Because if you have more electrons there, you have a greater potential. And pressure is basically like again like force per area, right? So it's like you have more things there basically, right? So positive value means that electrons naturally want to flow from anode to cathode. If it's greater than 0, there's something driving it along, right? If it's the opposite way around, then the driving force is in the opposite direction, which means you have to input energy for it to occur, right? So if you look at like all the stuff that we've been looking at, like all of these so far, you'll notice that like all the questions that we just did, they have a positive EMF value, right? The reason is because there's a driving force, like pushing it towards the cathode. Does that sort of make sense? Yeah. So a positive EMF means that you have a driving force, and therefore the reaction is going to be spontaneous. Whereas if it's not, then the force is kind of against it, and it won't happen spontaneously, right? Does that make sense, sort of? Yeah. Sorry?
They could put some nasty induction questions that people have no idea. Like strong induction.
What's an example of the? So when it's negative, it kind of just means that it's going to flow the other way, if that makes sense. Right? Because again, nothing sets the flow other than the electrons themselves, right? So if you set something up, like if you look at these ones, like here, right? If you like just to consider like um, if like let me think about how to like if like because for it to be negative, it's like imagine kind of like trying to force the electrons the other way in this reaction, right? Then you would have a negative EMF, right? Because you would have to be inputting energy to make it flow in the direction that you want, because that's not what actually happens, right? That's why it's non-spontaneous, right? You can see it. The reverse reaction of a negative EMF reaction will occur spontaneously. Does that sort of make sense? So naturally that wouldn't happen, right? But yeah.
So why does it happen in reverse? And if it does happen in reverse, oh no, okay, this is bad.
Yeah. Yeah.
Let's move on.
Oh, okay. Yeah, nice. So, yeah. So, like, if you look at the example on the next page, I think, if you look at, just very quickly, if we look at the example on page 22, you'll see that we have nickel plus magnesium 2 plus becomes nickel 2 plus plus magnesium, right? First of all, let's look at the reduction potential values. What's nickel's one? Okay, negative 0.26. What's magnesium? Negative 0.24. Okay.
I'll just keep up with it at tutoring in class.
Negative 1.1. So which one in this one is going to be reduced?
I went to the
Oh,
guy
yeah.
and
Which
said-
one's undergoing reduction?
I went in to switch it in there. I wanted to drop SOR. He said I'm taking
The one with the higher value,
system.
right? So
He
it's
said I'm trying to take advantage of the system.
nickel, right? But what's happening in this reaction? It's
Well,
undergoing.
I came in to drop SOR. I came out feeling guilty of a crime.
So typically in this reaction, between nickel and magnesium, nickel has stronger reduction potential, right? Which means that typically it would be reduced, right? But what's happening in the reaction that it's given to us? Nickel is going from nickel to nickel 2 plus, which means it's which means it's losing electrons, which means it's undergoing oxidation. This is the reverse of what we would expect to happen, right? So they're basically forcing this reaction to occur against its will almost. Right? That's why that sounded really bad actually. But like, yeah, anyways, like this wouldn't happen under normal conditions, which is why like this would be non-spontaneous, right? That's what I kind of mean by like you have to force the current the other way for like a non-spontaneous reaction. Yeah?
I don't want to do a
Does that make sense, everybody?
final HSC
Cool.
at the same time as my math.
That's basically it.
I could be using those 1.5 hours.
So there's what else is there? Yeah, so if you look at on page 24, it's basically talking about the use of platinum in a half cell, which I already kind of talked about. It basically just provides a surface for reaction to occur, right? Yeah. And then,
The last question.
yeah.
I think we
Wait,
saw
when you
it
say it's being
was like
forced
two
the other way,
spheres,
like
and there was like an intersection of the spheres in a circle. You get to show that like R squared.
Like,
R squared.
like,
Oh, yeah, that was the exact question.
Yeah, it was the exact same question. That was the last question.
like, I guess you could like
I didn't know before.
maybe force electron flow in the other direction. If you like apply an external current, you could force like electron flow in the other direction. But that's not something that would typically happen, right? Because again, like things will, like again, with this reaction, that's written in the book as the example that doesn't spontaneously occur. That's never going to occur, right? If you set because like if you like spontaneous, like if you set it up with nickel and magnesium electrodes, like this reaction is never going to occur. It'll occur in the opposite direction, right? Does that sort of make sense? Right? Because if you think about it, the EMF of this reaction this will be negative, right? The reverse reaction of this is going to be positive, right? So all this is literally just the reverse of the other reaction. Right? So if you flip the reaction arrow, it's true, and it occurs spontaneously, is basically the idea here, right? So like, again, the idea with spontaneity is if you were to leave this specific, if this reaction here just wouldn't occur if you set it up with a nickel and a magnesium electrode.
I feel like the HSC,
Yeah.
well, at least the HSC questions that I see as well.
Okay. Cool. Any other questions with galvanic test. Hopefully, you guys kind of get it. Obviously, like maybe go home and like do the homework, and it'll probably be some good questions to look at, and hopefully maybe look over it. Yeah, but hopefully you guys understand like to some extent. It is again, I think it's a difficult topic to understand, especially first time learning it. But yeah, cool. Any other questions? Any other questions with like the exam or anything like that?
What do you mean one for the final question? Like you sorted it?
No. Cool. Yeah, all right. You guys are free to depart.
Share this mistakes or just share this mistakes?
Wait, I was supposed to give you guys lollies, but I forgot. Everyone take some now. Everyone take some now before I was supposed to give you guys these, but they were sitting in front of my laptop. I didn't see.
Where's that top?
Who told you to give it to us?
Me. Yeah, I don't have to give it to you. Right? You can take more than one. Like, I'm not eating this.
I'll take it.
Yeah. Take as many as you want, guys. I really like these ones. Yeah.
Is it like
What are your favorite ones? Huh? Yeah, it's all time, guys. I want to go home as well. You guys.